in the material and actually probably start with neural networks, which is very exciting because that's really what the main class will be about a lot. Before we go, we had asked for feedback on Piazza, and thanks everybody who has already told us a little bit about what their thoughts are. Fortunately, the majority of people like the current speed. Of course, you have sort of the common dilemma for any lecture that some people think it's too fast. For those, please come to our office hours and ask lots of questions there. And of course, for some, it's a little too slow. In general, when I gloss over some of the math, so we went relatively quickly through some information theory type stuff in the last lecture. When I gloss over some of the math, it's in pretty much all cases just not that required for doing well in the class. It's often like food for thought for some of the advanced students. So there are some cases where some students are like, oh, this is boring and unnecessary, where, well, you know, if you give us a couple more weeks, you'll realize some of those pieces are necessary. In general, yeah, I think I want to make sure everybody understands the basics in the beginning. But basically, starting the second half of next week, we can become like more conceptual, introduce the actual complex models a lot of people use in practice, and then also gain some practical intuitions about, you know, doing this in large scale and so on. Also, I guess some people said the slides are a little too wordy, and maybe that was me compensating for not having lecture notes, so you can actually kind of make sense of the slides even without hearing a voiceover. But we actually have a new TA, Rohit. Maybe you can wave. So we'll have a new office hour, and also we'll start actually providing lecture notes. So probably with some delay, because you know the TAs will make a first draft and I'll go over them, and it'll take some time, but eventually we'll have lecture notes as well. All right. Also, given the feedback so far, we basically want to move the deadline for the problem set 1 by 2 days. You'll probably get all the last remaining details to then make it a little easier on you in Mondays, the beginning of Monday's lecture, depending on how fast we are today. So you'll have the deadline is plus 2 days into the future. A lot of people asked about projects, which is great. I'm excited that you're already thinking about the project. I think that will often be one of the most lasting sort of results of the class. If you have an incredibly good project, you may have a paper in the end, and that paper might be on your CV for the rest of your lives, and you actually contribute back to the academic community and so on. So that's great. For most of you, we'll probably have 2 types of projects. The first one is just taking the models that we introduced in the class and applying them to an interesting domain or a problem that you have, or some interesting data set. And the other one, which is a little more ambitious, is to come up with your own models and try to do some research. If you want to do those, please do contact me very early on and come to office hours frequently and start early, because that's much more ambitious. And if it works well, it will be great. You get a really good grade. But if you kind of stop short, and then it can actually end up much worse than just doing a solid project type 1. I'll go into a little bit more details of what that could mean next week. Also, right now we're still just covering the basics, so it's hard to think of really exciting projects, but we'll get there. And then one detail that I think was a great question that I could have made clearer is a little bit of the intuition of the context size. So we learn all these word vectors now, and one person observed correctly that as you get larger and larger context windows around each word that you're learning the vector for, the semantic scores get better, but the syntactic ones get worse at some point. And the main problem here is that if you have a very large context, right, and you essentially ignore the word order of the context, the larger the context gets, the less you know whether that word was actually in a position of a verb or an adjective or a noun, right? If I say 15 or 20 words to the left, and then I have 2 words in the center, good trip, or something like that. And now, good and trip will have almost all the context be the same if I have 15 words, right? It'll only differ by one word, and that's a relative, like only 1/15th difference now. So you get more information from the outside context, which helps your semantics. It helps, that word also appeared with like, fun, vacation, or things like that, which you wouldn't get from a small context, but you also lose the positionality. And that's what a lot of syntax captures, right? It's the position of a word inside a sentence. So on the other hand, if you have a shorter context, if it's extreme and you say, I really only have the left word, then all the nouns would essentially get similar word vectors, because all the noun knows is it happens after a determiner like the or a, like a trip or the trip or something like that. Or before, just after adjectives or something like that. So you'd capture only positional information. And then if you just have a very small context, like 1 or 2 words to the left and right, it very much captures where in the sentence that word appears. So verbs and nouns and so on cluster more similarly, or cluster together more. Are there any questions about or feedback or some additions people want to make? Again, if you haven't submitted your feedback yet, the link is on Piazza, and would very much appreciate it and incorporate it into the class. All right, so today we'll talk about some general classification background. One piece of feedback is that some of the notation isn't always clear, so we'll very clearly define what are our inputs, outputs, and so on. And then we'll actually go again over this detail that I tried to describe ad hoc in the last class, and that was maybe a little chaotic. So we'll actually very carefully try to understand what does it mean to backprop into words with a subsequent task after you pre-train the word vectors. And then we can actually move on to classifying windows, which is the first real model that will actually be useful for something that you might want to implement in real life. And then we'll very likely be able to define the first single-layer neural network or 3-layer neural network, depending on how you count. But we probably won't get all the way to the max margin loss and backpropagation, which is the main algorithm for this class. And really, it's just a nice word of saying we take more matrix vector derivatives. But it's a clever way, an efficient way of doing that. All right, so most of you are probably familiar with this already, so we can go through this relatively quickly. Here's a little refresher on general classification, the setup, and the notation that we'll use in this class. So in most cases, we'll have a training data set consisting of samples, where X is our input and Y is the output that we want to predict. For us in this class, a lot of the inputs will be words, which is less likely, and there's actually one important distinction here, which is if we backpropagate into the words, if we actually update the word vectors, then we would assume that the indices of the words are the actual input data. If we assume the vectors are fixed, then we can kind of just assume the vectors are the inputs. So that is an important distinction. What we more likely want to classify are context windows with the center word, or full sentences, or documents. And the sentence and document type stuff is what we'll cover in the second half of the lecture, or the whole class. The output labels YI is usually what we want to predict. It could be actually just other words, as in the case of word vectors, or something we'll cover next week, also language models, trying to predict the next word. In general, for most of the simple examples, we'll basically have a specific class that we want to classify. So is this word positive, or is this sentence positive or negative in the case of sentiment, or neutral? Or in the case of single words, is this a named entity of a type location or person, or something like that. But it can go as far, and I think that probably has been done by now, into saying more semantic or more important things, like should I buy or sell stock based on having read this specific phrase in the news just now. So for instance, Tesla had an April Fool's joke where they said they're going to release a new Model W watch, and they did that 5 minutes before the stock exchange closed, and their stock actually rose by like the largest amount since they had released some other car or something, and then it dropped an insane amount. So like a couple people lost a couple $100,000 or more probably. This is the highest the stock had ever been at that, like at the height, and then people realized the mistake or actually checked or so on, and then yeah. So these kinds of things happen, and in general, the class is it's basically up to your creativity what kinds of things you want to classify. Lots of fun things that you can do once you have all the tools for this class. You can classify whether this is a grammatical sentence, is this a good grade or a bad grade, and what's the answer to this question. Lots of fun things we can classify, including, and that will be sort of towards the latter or ending part of the class, multi-word sequences. So if we want to do machine translation, for instance, we don't just have like, this is English, right? That's obvious, but what is the actual translation of that English sentence into French or German or Chinese? All right, in the case of the standard one, which is just predicting the class, we'll basically have the following notation and sort of give some intuition about what's going on when we train logistic regression. You may remember from 229 that when you train logistic regression, you basically only get linear decision boundaries. So inside the exponent, you just have an inner product. And basically, assuming for now in the standard or general machine learning case that your word vectors are fixed, what you'd want to do is basically classify and divide your space. So here we have a binary classification problem. This is actually a screenshot from a really great visualization by Andrei Karpathy. It's called ConfNet.js. This isn't a ConfNet, but in general, this is what the library is called. I encourage you actually to play around with this. If you just Google ConfNet.js, you can play around with this and kind of gain an intuition of different kinds of classification algorithms. So basically here we just have a bunch of green dots. You could assume these are, for instance, two-dimensional word vectors. So you have here x1 and x2 are our 2 dimensions, and we have a couple of labeled examples, and we have basically our decision boundary here, and classify everything in this area as green. So here we have 2 or 3 points of the different class, but a linear decision boundary is not that powerful, and we'll have to make, in this case here, some misclassifications. So this is basically the general machine learning setting. We assume our word vectors x are fixed, and we'll basically just train the logistic regression weights w, and hence only modify the decision boundary. The inputs here, the dots, are basically set. You can't move them. In general, just to complete the notation, we'll again minimize our cross entropy loss function here over the data set. So we actually sum up all the points and then have the negative log of the softmax here. We'll actually introduce this notation and use that a little more in this class. So it's important to maybe write this down in your notes right now. So moving forward. So here, for each data pair xy, xi, and yi, we basically can define f of y as essentially a function of x that is just the yth row of our softmax weights w inner product with x. And that's just basically the sum here. So in general, when I drop the index I, so here we have yi, and here we don't. What I mean by that is we're just looking at one specific example. And then I can get away with using the index of x as xj here is actually the jth element of the vector x, and not like xi here, the ith entire vector. So xi is the ith sample, and here we abuse the notation a little bit, and xj is actually the jth element of the x sample. Does that make sense? All right, great. So in general, we can write f also in matrix notation, and that is something that we'll get introduced to today, is trying to think of these various notations and various operations that we do in terms of matrices, because that will be leading you to, 1, much cleaner math, and 2, much more efficient implementations. And I'll show you some code differences in Python to make you appreciate this a lot. So in general, obviously here, this is just the inner product with 1 row. So we can basically write out all the inner products for the entire f vector in matrix notation by just saying f is w times x. So just to check, what's the dimensionality of f? If we have capital C many classes, and we have n many data points, and each xi is d-dimensional. exactly, C. So because we have capital C many different elements of F, and W here has 1 to C many rows. Okay, so I also a little bit lied to you about saying that the cross-entropy error is our full and final loss function. Really, in practice, we will also have regularization, and that is going to be a pretty important part of the lecture. We'll actually talk about this a lot more, but just to give you a general sense for now, basically what that means is we will try to, as a prior, assume that thetas are better if they're closer to 0. Basically, if theta gets very, very large, we're probably overfitting to a specific data point xi, yi. And so this element here is basically our regularization. If theta, again, was a vector of all our parameters, one long vector, we basically square them and sum up all the squares. And lambda here is the strength of our regularization. So the higher lambda is, the more we want to push all the weights to be close to 0. Basically, that will allow us to prevent overfitting. And here's a very simple, high-level graph on describing overfitting. Basically, on the x-axis, we can have different kinds of things. We can have the number of parameters that our model has. For instance, the number of dimensions of our word vector. Or we can have the number of training iterations, or eventually, the depths of our neural networks. We have very deep neural networks. So basically, the more we are on the right, the more powerful or longer the model has seen the training data, or the more, it has gone over the same training data multiple times. And in blue here, we have the training error. So as we make the model more powerful, the training error will go down. As we train for more iterations, the training error will go down. As we have more deeper layers, and now that once we learn how to really optimize that function, the training error will go down. However, if we go too far on the side in any of those dimensions, oftentimes the test error or validation error, and you'll learn the difference next week, will essentially go up again. So maybe we can train very well to our training data, but now we can't generalize well to test data. Again, we'll go over this in more detail next week. But to give you a sense of what that means for the actual algorithms and the updates here, we again will contrast general machine learning, where we'll always assume our inputs x are fixed, versus deep learning. So in general general machine learning, our theta would just be the softmax weights, w. And we'll actually concatenate them here by just taking all the columns of W and stacking them into one long vector. I will sometimes use this notation moving forward. It's a little bit influenced by MATLAB, which basically, when we write this kind of notation here, we mean that we just take all the elements of a matrix and make them into one long vector. For instance, by taking all the columns and just stacking up the columns one under another. So in general, our theta here will just be a CD dimensional vector. And then our updates, of course, are basically only updating those weights. All right, so in deep learning, we now have this option to also learn the word vectors and take derivatives of our objective function j with respect to those. So instead of having a j that only includes w here, we'll also have basically all the word vector parameters. Yes?
Right, just a question. You said you're stacking columns, but then the symbols are put on top of each other. So I'm a little bit confused by whether we're stacking the columns.
Right. So you take the columns, and then this. So let's say this is your W, and now you just take each column and you stack them like this. Yeah. Good question. All right. So now we'll update here not just the W matrix, but also all the word vectors. So we have here actually a huge set of extra parameters that we're now optimizing over, right? So C is often, the number of classes you have. In named entity recognition, we have location, person, organization, and none of the above. So we have 4, and D might be 300. So we have maybe, 3 or 4 by 300. Now, our vocabulary, V, could be in the millions, right? So we could have 1 million different word vectors. And so, we made just with, times d, the dimensionality here could be 300 million parameters that we're adding to the model, right? So it's very, very significant. So what could be the potential danger that is immediately obvious once we have so many parameters? Exactly, we can overfit. So to give you an idea, the other problem is that, and that is a conceptual problem that I wanted to explain here really quickly on the board at the end of last lecture and probably wasn't doing a great job at, is that we're also modifying the word vectors. So as we update them, right, with the gradients here for each of the word vectors, we push them around in our vector space. And so let's, for instance, go through the example where we try to train a movie review sentiment classifier. And if in the movie just comes out and you say that should go straight to TV instead of wasting our time and money in the movie theater, it's just not high quality enough or something, then that would be associated with a negative outcome. So maybe if you have your word vectors, you learned them nicely, and again the word vectors will be higher dimensional. We're just visualizing this here to gain some intuition in a two-dimensional space. So assuming, for instance, telly, which is sort of the British funny British term for television, and TV and television here, they might all have similar vector representations because they might appear in similar contexts. As we start, and then we only train the softmax, and we may, in this simple case here, we get it right. Now, let's assume that in the training data, we only see TV and telly, and we never see at training time the word television. Right? Now, what happens when we train the word vectors? Again, originally using the word2vec model or glove vectors, the glove model, they'll all be kind of in the similar subspace in the d-dimensional space. So once we train them, we'll actually push around telly and TV maybe into some different part of the vector space. So before they were right here, and now maybe we push them over here. Now, of course, we also have to update our softmax based on the new word vectors, right? They go together. You update always both here. And so maybe now our decision boundary is here. And television, which isn't in our training data, but in the testing data, will basically stay where it is because we have nothing to update it with. It doesn't appear in the training data. And so television might now be actually misclassified, even though before it was correctly classified.
I don't know. So I can see what happens here, but should it be possible to, instead of retraining individual word vectors in isolation, train transformation of the word vector space that can generalize, so that if you're moving stuff that's similar in colors, you're also moving.
That's a great idea. I thought of this before. If you make that idea work, it would be a great class project. Here's one problem. Sometimes maybe your classification problem was, I want to classify British English versus American English. Now you update all of them, and you basically lose that ability. So it's tricky. Often, sometimes antonyms might also be close to each other. Great and terrible might be, might be close together. Now you update both, and you run into trouble. But maybe there's some way you could actually have just a small radius around the words and get away with it. Maybe it will help. Nobody, as far as I know, has really explored that. So could be an interesting class project, but high variance, because if you just ran some experiments and in the end it just doesn't work, and you learn that only 2 days before the paper deadline, then you just ran a bunch of experiments that don't work. So if you run that before the sort of milestone deadline, and you have a first sort of positive indication that could work, then let's go ahead. Yeah.
Even if it didn't work, wouldn't that still be a good result? We know that this doesn't work.
It's a good point. There are some interesting negative results sometimes. You're hard pressed to find an actual academic paper talking about things that don't work, because otherwise we would have to read 1 million papers more, because most of the things we try don't work in research. So it'll be a little bit in the eye of the TA or me. Probably I will grade most of the final projects, and at that point, it's not impossible to get still a good grade, but you'll have to then really show that you tried everything. Because saying something doesn't work can have multiple reasons. Maybe you just had a bug in your code, and that's why it didn't work. Maybe you didn't try hard enough and you didn't try the proper hyperparameter setting, and that's why it didn't work. So claiming something can absolutely not work is a pretty hard thing to do. You have to really cover all your bases, really understand the space, really understand all the reasonable options that some other researcher who might read that paper would have said, of course it wouldn't work because you didn't try X. And I was like, I've worked on X for many years, and that would have been the obvious thing to try. And then you get bad reputation. So like, likewise, maybe not a great grade. If you missed this one side comment I made in a lecture where you should try X and then you didn't, and so on. So, but yeah, in general, I do want to encourage you to try ambitious ideas. And if you try them well and you come to the office hours and we have enough feedback, then there's a good chance that even if the idea doesn't work, you could still get a good grade. Yeah, it's a good question. Yeah.
What happens with a cost function that includes both window similarity and the sort of training cost with like classification?
That is also a great question, and also leads to a potentially great project. Basically, you would then do a so-called semi-supervised learning. We haven't really gone through that in detail, but all this stuff that we're talking about here with classification is purely supervised. The word vector learning is in some sense unsupervised, right? You just take a bunch of text. You don't need to have a human go in and label, this sentence is positive, this sentence is negative, and so on. You just take all of Wikipedia. And so this is a semi-supervised learning approach, and that could actually work. The problem is that word vector learning can take many days. There are millions of word vectors, many millions of parameters. So if you just have your small little sentiment data set that has 10,000 sentences, and now every time you make an update on those 10,000, you now need to make an update on like 40 billion other tokens, then it just slows down things a lot. But again, there might be some clever ideas around that for a project. Awesome. OK, so this is basically the problem. So what's the take-home message here? If you have only a very small training data set, and you're basically at that point more likely to run into the problem that you've only seen a subset of the things that you really care about. In that case, you probably don't want to update your word vectors. You just leave them as is and use them and use the semantic similarities to your advantage. If you have a very large data set, on the other hand, that is likely to include all the things that you really care about, you will be able to fit that data set better if you actually update the word vectors. So to give you an example, sentiment is not that hard of a problem in the grand scheme of things, compared to machine translation or general question answering, which kind of subsumes everything else. Then in sentiment analysis, we collected a data set at Stanford a couple of years ago in one of my papers where we had 10,000 sentences, and every single subphrase of those sentences were also labeled. So we had 100,000 different labels for sentiment, and it was all only about movie reviews. We didn't look at finance and other domains. It was just movie reviews. At that point, we had so much training data, we could update the word vectors for our task to fit that data set really, really well and still generalize reasonably well. In fact, one thing we haven't talked about much here, the simplest thing you could do to your word vectors, if you have really a ton of training data that is supervised and for your task, is to just randomly initialize them. As you did, you just skip the whole word vector learning and learn them as part of your other model. But that is something you really only want to do if you have a ton of data for your task. All right, so that was basically the main takeaway message for, should you update into word vectors or not. All right, one side note slide here, and sorry for that being very wordy. Basically, sometimes throughout the class, I might use different terminology for word vectors. Basically, word embeddings and word vectors are exactly the same thing. And for pretty much all models except one or two, we can also call them word representations. And by that, we will just mean word vectors. The reason I say mostly here is that some nifty, interesting advanced models might actually represent words not just as vectors, but also as matrices. And so we might have that as a side note, but that's really just the exception. We often call this word vector matrix L the lookup table. And basically, again, it's just columns of the word vectors. And we'll use those word vectors as our features X word from now on. The very first time I read a deep learning paper, it said, and then we just take derivatives of the lookup table. And I'm like, lookup table isn't a mathematical, system. It's unclear how to take the derivative of a lookup table, right? And so just to give you an idea conceptually, if you really want to write out everything very properly and with proper mathematical notation, you could assume that one way to retrieve one column of your overall lookup table is achieved by basically left multiplying actually, I guess sort of right multiplying a one-hot vector E here by L. So E would be the size of your vocabulary. It's all zeros except at index, the index of the word that you want to retrieve. So let's say meta has, is the 500th column. You just at index 500 here, you have a 1. Everything else is 0 in E, and you multiply that on the right side here with L, and then you can essentially get exactly that column. Right, so it'll just be a d by v times v by 1 to get you a d by 1 matrix, vector out. Okay, so now we can move on to some stuff that you might actually really want to use in practice. Really, when I gave that example of classifying single words, that's really rarely ever done, because all the interesting stuff in NLP happens once you have a context. And so here are two interesting examples of ambiguity that arises in context. Auto-antonyms are actually a really fun phenomenon in language, and you can, if you enjoy this kind of stuff, you can think of others, there are actually a lot of them, where basically a word can mean its entire opposite as well as the main meaning that it has. So for example, to sanction can mean to permit something. So the Nevada State Athletic Commission, sanctioned some sport event, or it could mean to punish, right? Like some government sanctions some other government. So very much the opposite, and you'd need to know the context to really know which one is meant here. Or to seed can mean to place seeds into soil, or to remove seeds from a cherry so you can eat them more quickly afterwards. So again, the context here will tell you which one, which meaning is actually the important one or the right one for a given context. Another one that will actually come up in one of the problem sets eventually is for named entity recognition. Imagine you just have Paris, and your prior might be it's the beautiful city, capital of France, but maybe depending on your context, it might mean Paris Hilton. Or the Hathaway example that we already covered, where you have the company Berkshire Hathaway or the actress Anne Hathaway. And again, you need to know the context to know which Hathaway is being referred to. All right, so the main idea here will be to classify a word in its context of neighboring words. Again, NER, or named entity recognition, is one of those examples. And there are many different possibilities that you could think of on how to do that. And here again, I will glance over one model that we won't use, which is you just take all the vectors around that word, you average them all, and then you classify it. But really what will work much better is to actually, if you want to classify the center word, you concatenate all the words around that word. So let's go over an example here. So basically, you have, maybe you want to classify Paris. And so what you will do is you'll have a window length, maybe set to 2. That will take the left words, 2 words to the left, 2 words to the right of that word. And now X window will be your new input X to your logistic regression or your softmax classifier. So the resulting vector X window here will basically be a 5D dimensional vector. And just by definition, all our vectors are always column vectors. All right, so just a refresher here, the softmax, and we'll introduce actually some new notation as well. So X, when I write just X, then usually I mean X window right now. And we can basically use the same softmax classifier that we had before for single words, but now X is just a concatenation of word vectors. And we'll get from our softmax here the probability of Y given that X vector. And in terms of notation, we will actually call Y hat basically the predicted model output probability. And when we subindex it, we'll take that one element of that probability distribution, this multinomial distribution here. And we'll train this in general again with the cross entropy error as before. And again, this FYI here is just Y of W, the Yth row. Okay, so you've done this before, and you trained the W the W matrix before that we have here. but what about the word vectors? So the short answer is, well, you'll again just take derivatives, but because that is a really crucial part, and it's the first Lego piece that you'll then have to reuse many, many times in more complex settings, we're going to go over this, and I'll give you a couple of tips on how to do this, which will also help a lot for solving your problem set. So basically, here's the long answer, and the first thing to do is defining all our variables very carefully. So again, y hat will be the softmax probability output vector. And t is another notational convenience that will basically be our target probability distribution, which will be also a one-hot vector. So again, if we have four classes, for instance, and it's the third class, then our target might just look like this, 0, 0, 1, 0. And one thing that's important here, and it's a little lost in this notation, f of yi here, the I, yi is the correct label, is that f is really a function that depends on x. And as you take derivatives of multiple layered functions, you want to be very careful about keeping track of what variables depend on. And so yeah, so let's go through a couple of tips. In fact, if you at the end of this class, I hope that just from those tips you can kind of do all the math almost in your head, because it becomes hopefully sort of part of your standard thinking. All right, so tip 1, really carefully define all your variables and keep track of their dimensionality. So f of x is again a c-dimensional vector. Our W matrix is a C by, in our case, 5D dimensional matrix. So 5D because we have 5 words, each word is D-dimensional. We have here our y hat and our t, which are both C-dimensional as well. Y hat being our softmax outputs and t the target. Tip 2, know thy chain rule. That is very, very important. So don't forget, which variables actually depend on what. So one mistake you might make is, as you write out your first cross-entropy error for one element and one sort of training pair x and y, you may think, oh, only fy is in here. But really, in order to compute fy, right, you had to have all the other fc's as well in the normalization. So basically you'll have to sum over these. So we're taking here the derivative with respect to x, and so x actually appears in all the different elements of the vector f. So we'll basically have to sum here over all our classes the negative partial of the log softmax with this with respect to each of the fc's, and then times the derivative of fc with respect to each of the x's. And this is basically line 1 on one of your problem sets. The next tip, for the softmax part of the derivative, it's and in general, it's very helpful to first take derivatives with respect to some elements and basically tease apart if they're two different cases. So if C, for instance, equals exactly the correct class, you'll get a different derivative with respect to that fc compared to taking derivative with respect to fc when C isn't the correct class. So that will then lead to something that looks like this. What often helps is to write out the partials of some of your elements into basically a vector notation. So you can take first the derivative of f1 and then f2 and f3 up until fc. You write them all out, and then you can maybe observe some pattern. And this here kind of looks a little ugly. Now, if we wanted to use this later and say, oh, I want only the jth index of this vector, then that it would look very ugly very quickly. So in order to not go insane, and also for much more efficient implementation, you're going to want to write your everything in terms of vector operations. And this is where our convenient vector t, the target vector, comes in, which basically we can just write this y is basically just the entirety of our prediction vector y hat. And if we write minus t, then we just have here minus 0, and for the correct class y, we have minus 1. And we can now define that negation or summation here in terms of one specific other variable that we'll call delta. Okay, so now last slide on all the tips. And sorry for those 15% of you who have already finished this and so on. So basically, tip 5, when you start with the chain rule, it's very good to often take sort of explicit sums and look at the partial derivatives with respect to sub-elements of the overall matrix or vector that you're taking derivatives with respect to. And so in our case, as you write this out, you'll basically get the sum here, delta C times the different rows of our W matrix. And this one here, this derivative is very, very intuitive. So you just had, derivative of FC with respect to X, and that was just an inner product. So you just get a row vector out if you take the derivative of this here with respect to X and just one of the rows. But now this one is kind of not very efficient in terms of implementing it. In general, as you implement things, you want to have as few for loops as possible. This is a general rule, and I'll show you why in a couple of slides. But basically, you want to clean this up and make the notation simpler, but also your code more efficient. And basically, you can see that this actually just becomes exactly this multiplication here of W transpose times delta. And if you don't, if this doesn't make sense to you, then write out all the sums and see that in the end they're actually exactly the same. All right. So what's the dimensionality of this matrix multiplication? Say again? Exactly, 5D. Because X is our window and X is 5D, our gradients for the window X have to have the same dimensionality. So this is actually also the first step of implementing. When you implement something and then it crashes because the dimensionalities don't match, you know you have a bug in your code. Once they match, then it's actually getting harder and harder to mess it up still, but you can still do that. And so we'll actually in the next lecture give you a tip on how to know that your code for sure has no bug, which is kind of amazing in the grand scheme of things, because these are complex models, and we'll actually with finite difference gradient checks we'll be knowing for sure that there will be no bug in the hardest part of our code. So in many ways you can check and already know if you get the right grade or not, or the highest grade or not for a lot of your assignments in the future. All right, so basically the gradients that we arrive at that update the word vectors are now for the entire window. But of course, we don't have our window. That's not what we eventually want to store, right? Because there would be lots and lots of different unique windows that would have to learn vector representations for. Instead, what we usually do is, we actually have the word vectors with which were just concatenated to get the window. And so really what this delta of the window is, or delta x window, we're missing an x here, is basically just the gradients with respect to all the vectors that were part of that window. And so basically what we can do is just update the specific vectors with those specific elements of the gradient. Yeah?
What do you do if a word appears in your text what do you do if you word like that?
That's a great question. So what do you do if a word only appeared in training and never in the test set? It's a really great question. In fact, it's probably something we'll have a couple of slides for, just because there are actually different options. Just really quick, the first option would be you actually train an unknown word vector. And you just take all the rare words, even in your training corpus. You don't learn vectors for them, and you just say they're all the unknown words. And then you can do that for unseen test words. That will be the simplest answer. All right, so basically that will allow us now to push the word vectors around into areas such that they're really helpful. So to gain some intuition here, let's say we had this example of, museums in Paris are amazing, then maybe now what this model could learn is that when you see the vector for x in just before the center word, so just in this specific location of the window, that could be very indicative for the center word to be a location. So these are the kinds of things that the model could now pick up. What it can't really pick up is how do these words really interact. OK, so what's missing for training this window model with our derivatives so far? Maybe this is too easy. It's of course the softmax weights. So we've only talked about the gradients for x, and of course you also have to update your softmax weights. So the final update that you'll have for your cross entropy error in a model where you decided to update the word vectors is basically this equation here. All right, one really important note on matrix implementations. I've seen some questions, I think some of them are private on Piazza, on matrix implementations and the code being very slow. Basically, there are two expensive operations for the softmax, right? The first one is the matrix multiplication, and the second one is the exponents. We'll actually find probably later in this lecture or early next lecture a way to get rid of several of the exponents, which is going to be great. But the matrix multiplication will always stay there, and it will always be the case that that is the #1 bottleneck for all our deep learning models. So there's at least one way you can make them more efficient, which is try to avoiding for loops. Basically, whenever you could implement a for loop, it won't be as efficient as if you could do the same mathematical operation in terms of one large matrix multiplication. So let's go over an example here. So this is some code I just hacked up really quickly, which is kind of fake. There's no real data in here, but it gives you an idea of what's going on. So you have here n is the number of windows that we may want to classify. D is the dimensionality of each window. And C is the number of classes that we have. And these are not totally unrealistic numbers. Maybe if you have larger training data sets, eventually this will just be one subset of your data that you're updating over. Now, our W will just be, in the simplest case and the simplest initialization, just a random matrix of C times D dimensionality. And now we have two options, right? We can have all our windows be a list of separate vectors. So just here, obviously these would usually come from your word vectors, and you would concatenate them manually instead of just randomly initializing the windows themselves. But just to create that data structure here, this would be one way. Another one would be you take all your concatenated window vectors and you actually put them together like this. So instead of having a list of different vectors, you will just put them all into one very large matrix, right? And now what you can do is you have the two options based on these, right? One is you just basically classify, you multiply W times your input window X, right? So this is just the equation that we always write for the softmax before you take the exponents. And this is to compute your feature vector or your vector F. Or we could basically multiply W times this entire matrix here, right? And those two things are exactly equivalent. They're the same thing. And this one here, though, will take you 640 microseconds, and this one only will take you 53 microseconds. So it's a lot more efficient to be able to basically make one large matrix multiplication compared to lots of little small vector multiplications, even though mathematically, obviously, they're the same. And this will be even, the speed difference will be even bigger the bigger matrices you have, because essentially down inside Python, inside a lot of other packages, they can parallelize. You can parallelize the matrix multiplications very, very easily. And the larger the matrices are, the more you can parallelize. And that, in the extreme case, will lead us to graphics cards. Some of the newest graphics cards from NVIDIA have 5,000 cores. So now you could make this really large matrix multiplication in almost 5,000 different threads. So you can get speedups where your code on a CPU might take 9 hours, and you put it on a GPU, you vectorize everything, everything is a large matrix multiplies, and it takes only half an hour. So it's a really, really important implementation detail, and I'm tempted to almost like subtract points even if you have the right solution, but you don't have it nicely vectorized in your p-set, but maybe not. All right, so basically, yeah, this is what I just said. Each column now of this resulting matrix is one f of x, and you can now think of, how would you essentially use that matrix to do everything else. Now you take exponents of everything, and then you divide by the sum of each column, and so on. You can do everything in that matrix. You don't need to ever go over for loop over your samples, as long as your models are these kinds of standard feed-forward kinds of models. All right, so matrices are awesome, and I also encourage you always, if you have two options, you're like, oh, I could implement it like this, or I could implement it like that, always try and just use the time-in function in either in Python or whatever code you have. Just write a for loop that does something 50 times, sum up the time, and compare two different implementations. Helps a lot in the speed. All right, so this has basically been all the linear stuff that we had to do, and now we can finally get to some more powerful models. As we mentioned before, softmax is only ever going to give us linear decision boundaries. So if you have, for instance, this is our space here, and we had a bunch of data points in the red class and the green class, everything that is, everything that's green, green dot here that is in the red area is misclassified. And if you have enough data, that would be pretty lame. Right? So it would be really awesome if we could actually learn that part of this space right here actually is indeed still green, and maybe up here this is a different class again. And so what we will now be able to soon do is essentially use neural networks that will learn arbitrarily complex decision boundaries. Well, not arbitrary, depending on how large your neural network is, but in general, they'll be able to learn much more complex functions and very nonlinear decision boundaries. And that is really like you sort of level up in your skills once you really understand this and can implement this. So let's move from logistic regression to neural networks and define some of the basics. Again, this will be, kind of just defining a lot of terminology, going over maybe the boring basics. But once you're really down with that, we can do a lot of really fun stuff in the next couple of weeks. So again, they'll just come with some terminological baggage, like support vector machines and so on. Basically, we will define a single neuron. This is usually how we visualize it or illustrate it. It will have certain inputs, have an activation function and an output. And it will also often come with a bias unit, which in other terminology, other subfields, is called the intercept term. And the cool thing is, now that we really understand the softmax, and you can almost in your sleep take derivatives of just the softmax that we've had before, you'll be able to understand the operations of basic neural networks very easily also. So a single neuron, this is essentially the equation for a single neuron. So we have here, again, a simple inner product plus a bias term. And then we apply what we call a nonlinearity f. So this f here is an element-wise function that basically just takes a single number and returns a single number. So here, for instance, we have the sigmoid function that we had used in the word-to-vec model. And yeah, B can essentially kind of be interpreted as an always-on feature. So one way to make that more efficient, for instance, into matrix multiplications is to just add a 1 to your x vector every time, and then add an extra element that you initialize to 0 to your w vector, and now you'd have just one inner product instead of an inner product plus some other bias term. All right, each neuron basically has these parameters here, which are this vector w of weights and the bias. So now we can feed a vector of inputs, like a word vector or a window vector, through a bunch of logistic regressions. So instead of just having one right away and making a final classification, we feed them into multiple different logistic regressions. And then we get, again, a vector of output. And now the sort of interesting part for all the models moving forward is that we won't actually have to decide what exactly each of these neurons has to compute. It's not, we don't really require this to be a probability for a specific class. We could now take the inputs or the outputs of those units and feed them into another logistic regression or softmax layer. So this, again, could just be a softmax, but now the softmax sits on top of a softmax, which sits on top of your input vectors. And now, depending on what loss function we have here, which could, again, be the same cross-entropy pair we've used before, we'd basically tell these so-called hidden units, hidden variables, what they should really be capturing in order for us to do well on the final classification problem. And we'll go over those in a lot more detail. So this is sort of a high-level overview. All right, so basically, before we know it, we just had a bunch of little logistic regression units. We put them all together, and we'll have a neural network. And what these actually mean, and how to select how many layers you should have, and so on. We'll go over all of that throughout the class. So let's define a little bit of matrix notation here. So basically, we can say we'll have first a linear type layer and then a nonlinear layer on top of that. So if we had here our word vector or window vector, we just have the standard wx plus b. This is basically similar to our logistic regression or our softmax, but now instead of actually normalizing over all of the z's, we'll just have an element-wise so-called nonlinearity. And when we write f of z, and z is a vector, and we know that f actually only takes in a single real number, what we usually mean is that we'll basically apply f element-wise. So f of the vector z1, z2, z3 is just f of z1, comma f of z2, and so on. All right, so this is just the main notation. And now, I sort of hinted at this in this figure before, but you could say, well, do we really need these nonlinearities? As we, if we just had, w1 times w2 times w3 times x, for instance, it turns out that at that point, if we at the end of a bunch of linear matrix multiplications, we would just have the softmax after that. We would still only have a linear function. It wouldn't really give us any power, and we wouldn't be able to create these kinds of decision surfaces. So without the nonlinearities, deep neural networks wouldn't be very powerful at all. It'd still just be linear transformations. And so intuitively, if we were to do classifications, this is the kind of more powerful decision surface we'll get. If we were to do regression, then if we just had one hidden unit, we could just basically have here an inverted sigmoid-like shape. But once we have multiple hidden units, we'll actually be able to fit our data better and better. Up until with enough hidden units, we can basically overfit almost any data set out there. So that leads us to a much more powerful window classifier. So we'll basically revisit this idea of trying to classify here a word or, in some cases later on, just a general window. And instead of taking this vector and directly inputting it into a softmax, we will first multiply this vector by w and add a bias term, and then look at the activations, we often call A the activations, by basically applying this element-wise function. Are there any questions about this so far? Yeah. Yeah, so that's a great question. So right now, I just mentioned that we'll have the sigmoid kind of nonlinearity that would be used in a binary logistic regression, but it's a great question. We'll have, I think next week when we look over a bunch of tips and tricks, there are actually lots of different options, and it turns out they don't have to go only between 0 and 1, and they don't need to be interpreted as probabilities. They can be lots of different kinds of functions. So yeah, we'll go over that a lot. Yeah.
Would we do for deal with this computations or something by doing this anti-data recognitions, or should we just our outputs generate like script or something?
Sorry, I couldn't understand your question.
Do you deal with punctuations like commas or?
Oh, right, yeah. So does punctuation have a vector associated with it too? And the answer is yes. Especially if you want to learn word vectors on Twitter, for instance, you better keep around, you know, all the colons and parentheses and stuff like that for smiley faces and so on. Yeah. And even the sentence final punctuation mark is very indicative for certain patterns. All right, so basically now that we have this, this vector A, so A will be a vector that depends on the dimensionality. So let me ask you this. Let's say I wanted to have a vector A here that has 100 dimensions. What dimensionality, and let's say my x vector is a 300 dimensional vector, and I want A to be a 500 dimensional vector. What would the dimensionality of W, which essentially defines our first layer of a neural network, what would it have to be? Say again? Exactly. 500 by 300. We multiply here this 300 dimensional vector with 500 by 300 matrix. And then we apply this element-wise nonlinearity to every single element of that resulting vector. All right, so now once we have this vector A, we can kind of assume that this vector A is essentially the set of features that we actually use to now make a classification. So we could just put A into the same old softmax that we've had before. But one of the problems with the softmax was that it was essentially a little, one, it was slow because we had to take exponents. Exponents are actually a relatively expensive operation. And two, they basically spend all this time normalizing, right? You had this normalization factor that sums over the exponents of all the other classes and their f's in that case. And so one thing we can actually instead do is maybe just compute a single score. And that score doesn't have to be normalized. It's just if that score is large, you know, and we just had a binary classification problem, large scores mean one class, small scores mean another class. So similar to an SVM, we just don't have here probabilistic interpretation. So we can now compute the score of a window X as just the inner product U transpose times A. And that, again, will just be a single number. So let's put all that together and define our very first 3-layer neural network. And the reason I say sometimes 3 and sometimes 1, and it's actually still up, in some ways it's not really that important of a debate because the math disambiguates it very clearly. But some people call this kind of model a 3-layer neural network because it has an input layer of the word vectors. We'll now have one hidden layer, and we'll have one output layer. Other people say, well, that's kind of overdoing it. Really, you have one hidden layer, and all the other stuff is sort of standard non-deep learning kinds of machine learning, and they just call this a one hidden layer neural network. So maybe that is one way to disambiguate it. You could say a 3-layer network or a one hidden layer neural network. All right, so let's say we wanted to classify here that this phrase right here is, for instance, positive, or it's a grammatical phrase. So we can really classify this window as anything you want. You can define the score that comes out here to be, this is very likely to be a location, or this whole phrase is a grammatical phrase. Really, it depends on you. And if you have enough training data, the model will essentially be able to figure out what it needs to get as input in order to make that kind of classification. So in the simplest case here, we won't use a softmax. We'll just have an inner product to get a score. And this is basically the definition of our neural network. Could you raise your hand if all that notation makes sense? All right, great. So let me ask you, what should the dimensionality of U be if A was 500? That's too easy. That's 500 too. So let's make it a real example here. So let's say each of our word vectors x is a 4-dimensional word vector. So now the total here will be a 20-dimensional vector, and we have here an 8-dimensional hidden layer. Now our W will basically have to be guess we asked a similar question here. It will have to be an 8 by 20 dimensional matrix. And of course, our B here will have to be 8-dimensional as well. And then we apply the nonlinearity, and our U is essentially just a vector. In most cases, my notation will be such that vectors are actually lowercase letters, but if that letter actually defines the whole layer, I sometimes change the notation and make it also a capital letter. So basically, we can now compute the score of this entire window with this function right here. Yes?
In practice, do we often choose A to be this dimension of A to be lower than the window dimension?
That's a great question. How do we in practice choose dimensionality here of the hidden layer? Boy, it's actually the full answer will be a lot more complex, and we'll go over that in a lecture 2 and have a couple of slides on that. In many cases, you do reduce the dimensionality. Yes, but sometimes you can actually show that there's some very interesting results and visualizations that show that will not allow the model to do certain things. So there are some exceptions where we actually want to blow up the dimensionality first and then reduce it again. And that will kind of depend on how complex your problem is, what kinds of different things you want to classify, and so on. All right, so I thought we were going to do this in the next lecture, but we still have 5 minutes. So maybe I'll just define. I'll define the first three or so slides, and then we'll talk about backprop and actually optimizing that model in the next lecture. So so far, we've really had only softmax and cross-entropy errors, and that is usually a combo, right? You have a specific type of output layer. Softmax for us will eventually just be a type of layer, and that output layer comes with a certain way to optimize the overall function or the overall model that we have. But like I said, we don't always need probabilities. Sometimes these unnormalized scores are enough. And we sometimes want to have max margins, a max margin objective function. We'll talk about max margin learning a lot more. There will be a lot more examples on that. But intuitively, if you decided, if you had to decide between any this is not our class. My office hours are right after class and gates 200. If you had to decide between two objective, let's say you had just a very simple binary classification problem, and you had the option to now have a decision boundary that looks like this, then that would be a very suboptimal decision boundary, right? And again, these are basically here. This is the normal, and so on. You might want to look up like 229 if these kinds of plots don't make sense to you. But my hunch is given who raises your arms and so on, this is very intuitive. So in general, softmax, this would be an OK decision boundary true. But really, it would be a suboptimal one, because maybe you find at test time another x that will be very close to that one, but right here, or another of this class right here, and that one will be very close to this one. So really, a much more robust decision boundary, and one that max margin is much more likely to give you, or max margin objective function will be this one, which will essentially maximize the distance of any of the points to that margin. And so at test time, we have things that are roughly close to our inputs are much more likely to get classified correctly. So we'll go over that in a lot more. We'll actually have very complex structured max margin losses in the sort of couple of weeks. But basically, the neural network model that we'll go over and really in all its gory details define derivatives in the next lecture will be a max margin loss function. The main idea is that we train a neural network to essentially try to produce high scores for grammatical phrases of a specific length and low scores for ungrammatical phrases. And how do we get training data? Well, this sounds like a supervised problem, but we can actually make it very easily into an unsupervised kind of problem by just taking windows of words in, again, Wikipedia, and replacing the center word with a random word. On average, in most cases, that will result in an ungrammatical window. So for instance, we have the phrase cat chills on a mat. We say, all right, we would like to have this window receive a high score. And then we replace the center word with a random word, maybe Menlo, and say cat chills Menlo a mat. And we would like to get this corrupted window get a low score. And our objective function here will be looking like this. And again, this is the objective function j for a single window. Eventually, we'll sum over all the windows here. So basically, the idea is that we want the score of the true window to be larger up to a specific margin. So let's look at this here. We try to minimize this, and the score here is negated. So we basically maximize the score of the correct window. And then we minimize the score of the corrupted or incorrect window. And the nice thing about this objective function here is that if the model has gone over a couple of windows and it's already assigning the correct score, to be 10, and the incorrect score of, the counter pair here that we just created on the fly by going over windows, if this is already 10 and this is only 5, then the model can essentially already correctly distinguish between the two. And in that case, the max here will basically say, well, this is 0. The max of 1 minus 10 plus 5 is smaller than 0. So the objective function here will just basically care about the 0 and be done with that training example. So as you train over time, you need to look at less and less of your data to actually compute derivatives for. You just compute forward propagation or compute your scores here. And then that you don't need to back propagate into this. And basically what we'll start in the next lecture is to really take the derivatives of all of this. And that will be the last lecture where we have to go through tons of equations, because really everything else after that falls out of these, and it'll be special cases and combinations of the kinds of Lego pieces that we've learned about until now. All right. Oh, sorry, we have one question. Yeah.
You have the possibility here to make way more corrupt data than you have uncorrupt data.
Yep.
Let's suffer less from the biased data problem.
That's a great question. So we could, in theory, for every single window, we could create tons of corrupted windows that are incorrect. And in some ways, it's a trade-off. And it turns out, in the end, it doesn't matter. If you take 500 corrupted windows, it takes you longer to go through them, but each one does better. But if you just go over more windows, you kind of get a similar effect. All right. Thanks. See you Wednesday.